Hi, this is Victoria Kabat, and this is my Lab 5, Faraday's Law. So, as an introduction to this lab, the purpose was to learn how time-varying magnetic fields affect electric fields and induce currents. So what we did was that we used a bar magnet and dropped it through an aluminum foil tube to model magnetic fields changing during time, which also modeled Faraday's law because the bar magnet's motion is affected by the presence of the conductive aluminum foil, which therefore slows down the fall time. So my results showed that my experimental fall time was 1.238 seconds, and my computational fall time was 1.149 seconds. So the physics principles involved in this lab were the PHYS law for a single charge, and this is the basis for the magnetic dipole equation. And then we also used Lenz's law, which says that the direction of induced current opposes the change in magnetic field that produces it, and Faraday's law, which says that changing magnetic flux induces a current. So the process began by using the magnetometer app, which we used to mark the north end of the magnet, and then I recorded 5 trials of dropping the magnet through the aluminum foil tube, and this started with the vertical end of the aluminum foil tube, and I dropped the magnet down and recorded this on a video, and then scrubbed it to get an entering and exiting time for my bar magnet. So using that, I found 5 trials and 5 drop times, and then I averaged them to get an experimental fall time of 1.238 seconds. My computational method was next, and I started this by defining the aluminum foil tube measurements, and then I did the next step, which was finding the magnetic field function, which I used in lab 3, and then after that, I calculated the magnetic flux function. And then after that, I calculated the current for a single ring, and then I calculated the B fields for all the rings. And then I defined lines in my code to define the net force, the velocity, the time, and the position of the bar magnet. So when I run my code, this is what appears. So my computational fall time was 1.149 seconds, which is faster than what my experimental fall time was. And to the right, you can see the model of the aluminum foil with a red bottom, which is representing the bar magnet, and then a graph of velocity versus time of the bar magnet's drop. So some computational interpretations were that the coloring of the magnet, whether it was blue or red, showed the current's direction. So my current was red, which means that it was clockwise. And if the magnet flipped around, the dynamics would be flipped for the entire system. So the magnetic flux and the induced current would also flip. And then the total time effect differences shown experimentally versus computationally show that the aluminum foil tube's conductivity and air resistance aren't being accounted for computationally. Therefore, it's faster in the code than it is in real life. And then the graph plot of velocity versus time eventually flattens out, which means that the F net is equal to 0, which says that gravitational force and magnetic force are equivalent during that time period. So some result summary, I found that my magnet's fall time was slowed down by the presence of the conductive aluminum foil, and my experimental fall time was 1.238 seconds, and my computational fall time was 1.149 seconds. And when I calculated the percentage difference of these two times, I found that they had a 7.75% difference. And in conclusion, if the resistivity of the conductor were reduced as close as possible to 0, the dynamics of the falling magnet would completely change. So the fall time would therefore increase, the current induced by the magnetic flux would also increase, and therefore the magnetic force would also increase. And if holes or slots were cut into the tube, the ring currents in the model would be changed because the fall time would decrease, the current induced by the magnetic flux would also decrease, and because there are smaller numbers of rings, the resistance would increase, and therefore the magnetic force would decrease. So thank you so much for listening, and if you have any comments or feedback, please let me know. Bye-bye.